Welcome to the boundless mystery of the universe, a universe far more complex and elusive than we may ever fully comprehend. We look up at the night sky and see stars, planets, galaxies, things that feel familiar, even if distant. But what if I told you that all these visible, tangible things make up only a tiny fraction of the universe's true nature? Beyond what we can see, touch, and measure lies something so mysterious, so perplexing, that it defies our current understanding of physics. Imagine a force that fills the vast stretches of space, a hidden mass so immense it outweighs all the stars, planets, and galaxies combined. Yet it's invisible, undetectable in any traditional sense. This force silently influences everything we know, subtly guiding the formation of galaxies, bending light, and shaping the very fabric of space. Scientists call it dark matter, a fitting name for something that lurks beyond our perception. And then, beyond the mystery of dark matter, we encounter another enigma that shakes our comprehension even further: dark energy. This strange force is not just an unseen player in the cosmos, it's actively pulling the universe apart, expanding it at an accelerating rate, pushing galaxies farther and farther from each other. What could possibly power such an unstoppable force? The existence of dark matter and dark energy forces us to confront the limits of human knowledge and imagination. Our familiar theories, the formulas we trust, and the rules that govern our everyday reality begin to unravel as we confront the profound mysteries of these invisible forces. What we're about to explore is a journey into the heart of these cosmic enigmas, stepping into realms where science meets speculation and reality borders on the surreal. Together, let's venture into the mysteries of dark matter and dark energy and dive into the cosmic puzzle that continues to mystify scientists, philosophers, and explorers alike. What we uncover might just reshape how we see ourselves and our place in this vast, mysterious universe. In the vast theater of space, our understanding of the universe has grown immensely over the past few centuries. From early observations of planets and stars to Einstein's theories, each scientific breakthrough has expanded our view of the cosmos. Yet, amidst all these revelations, a deeper mystery remains, one that's invisible, elusive, and yet holds the universe together. This mysterious substance is dark matter. So what is dark matter? To put it simply, it's a form of matter that does not emit, absorb, or reflect light, making it completely invisible. Imagine a material that doesn't interact with electromagnetic forces, the very forces that make atoms, light, and everything visible possible. Dark matter is thought to make up about 27% of the universe's mass energy content, while all the stars, planets, and galaxies we observe account for less than 5%. This means that most of this stuff in the universe isn't stars or galaxies. It's something hidden, something we can't directly observe. Our story of dark matter begins in the early 20th century with observations of galaxies and the motion of celestial bodies. Astronomers noted strange behaviors in galaxies' movement that couldn't be explained by the visible mass alone. Stars on the edges of galaxies were moving at incredibly high speeds, speeds that defied the gravitational pull that should be exerted by the galaxy's visible matter. This wasn't just an isolated case, it was a pattern observed in countless galaxies across the universe. For this movement to make sense, scientists realized there had to be something else present, an unseen mass exerting gravitational force, keeping galaxies bound and stars moving as they were. They called this unseen mass dark matter. One of the pioneers in discovering this mystery was Fritz Zwicky, a Swiss-American astronomer. In the 1930s, Zwicky studied a galaxy cluster known as the Coma cluster. He calculated the mass required to hold the cluster together based on the movement of its galaxies. The visible stars simply couldn't account for this mass. There had to be something more, something hidden that held the cluster together. Zwicky's findings were revolutionary, suggesting that we were missing a huge part of the universe's mass. As years went by, Vera Rubin, an American astronomer, further explored this concept. Rubin's work in the 1970s examined the rotation curves of spiral galaxies, specifically studying how stars moved in relation to the galaxy's center. Rubin and her team observed that the stars farther from the center weren't slowing down as expected based on Newtonian physics. Instead, they maintained a speed that implied the presence of much more mass than what was visible. Rubin's research solidified the idea that some unseen force or mass, later called dark matter, was keeping these galaxies from spinning apart. But what exactly is this dark matter made of? Scientists don't yet have a definitive answer. Since dark matter doesn't interact with light or electromagnetic forces, we can't observe it through traditional telescopes. It doesn't emit or absorb radiation, making it invisible to all forms of electromagnetic observation. Instead, we infer its existence through its gravitational effects. Dark matter might be composed of particles that are fundamentally different from the ones that make up visible matter. The most widely accepted candidates for dark matter particles are known as WIMPs, or weakly interacting massive particles. WIMPs are thought to be massive, yet they interact only through gravity and the weak nuclear force, which is one of the four fundamental forces of nature. These properties make WIMPs incredibly hard to detect, as they barely interact with other particles. Experiments around the world are currently underway to try and detect WIMPs directly. Huge underground detectors shielded from cosmic radiation are waiting, hoping that a WIMP will interact with their highly sensitive equipment. So far, no conclusive evidence has emerged, but each experiment brings us closer to understanding dark matter's true nature. Another potential candidate is axions. These are hypothetical particles that are incredibly light and, like WIMPs, don't interact with light or electromagnetic forces. Axions would be difficult to detect, but if they exist, they could explain some of the gravitational effects we attribute to dark matter. Axions also have properties that might help explain certain behaviors in quantum mechanics, adding an extra layer of intrigue. Dark matter is also essential in the process of galaxy formation. Without it, it's likely that galaxies would not have formed in the way we see them today. Dark matter is thought to act as a kind of scaffolding in the early universe, providing the necessary gravitational pull to attract regular matter and eventually form galaxies. When we look at simulations of galaxy formation that include dark matter, the structures that emerge closely resemble the actual distribution of galaxies in the universe. This cosmic web, as scientists call it, is evidence of dark matter's role in shaping the universe on a grand scale. Gravitational lensing provides one of the most powerful tools for studying dark matter. When light from a distant galaxy passes through a cluster of galaxies on its way to Earth, the gravity from the intervening cluster can bend the light, causing the distant galaxy to appear distorted. By studying these distortions, scientists can map out the dark matter in the intervening galaxy cluster. This method has provided some of the strongest evidence for dark matter, showing how it clumps around galaxies and forms structures that are invisible to the naked eye. And so, here we are, searching the universe for something we cannot see, hear, or touch, yet something that we know must exist because of its undeniable gravitational effects. The search for dark matter is one of the most profound scientific quests of our time, pushing the boundaries of what we know and challenging the limits of what we can discover. In essence, dark matter is a cosmic mystery. It's a reminder of how much there is left to explore and understand. Every advancement we make, every new discovery, brings us closer to unraveling this enigma. The search continues, with scientists around the world using particle accelerators, underground detectors, and gravitational studies to look for clues. Dark matter may yet remain elusive, but the search itself is a testament to human curiosity and the drive to uncover the secrets of the universe. Perhaps one day we'll be able to answer the question, what is dark matter? Until then, we journey deeper into the unknown, armed with the knowledge that even in the vastness of space, the most extraordinary mysteries lie waiting for us to uncover. Dark energy is a force unlike anything we experience or understand fully in our daily lives. Imagine for a moment that, instead of gravity pulling everything inward, an unseen force is actively pushing galaxies apart, accelerating the expansion of the universe. This is the perplexing reality of dark energy, an invisible entity that not only permeates all of space, but also exerts a repulsive force on it, counteracting the gravitational pull that typically brings objects together. To grasp dark energy, it's essential to first look back at the history of our understanding of the universe's expansion. For centuries, scientists believed the universe was static, neither expanding nor contracting. This idea persisted until the 20th century, when astronomers like Edwin Hubble observed that galaxies were moving away from us in all directions, indicating that space itself was expanding. This discovery was groundbreaking and led to the widely accepted concept of the expanding universe. Yet it wasn't until the late 1990s that scientists discovered something even more startling. The rate of expansion was not slowing down as expected due to gravitational attraction. It was accelerating. This unexpected observation turned our understanding of cosmic forces on its head. When scientists studied supernovae, massive explosions of dying stars across vast distances, they noticed that distant supernovae appeared dimmer than anticipated. This observation meant they were farther away than expected, leading to the conclusion that the universe's expansion was accelerating. This was completely unexpected, as gravity should naturally cause the expansion to decelerate over time. So what could be driving this acceleration? Scientists hypothesized the presence of an unknown force, which they called dark energy. Dark energy makes up about 68% of the universe's total mass energy composition, vastly overshadowing visible matter, dark matter, and all observable structures in the cosmos. Its influence is so pervasive that, despite our lack of direct evidence, we see its effects on a cosmic scale. It is fundamentally different from dark matter. While dark matter is thought to exert gravitational influence, helping to form galaxies and structure the universe, dark energy is a repulsive force, pushing everything apart. There are several prevailing theories about what dark energy might actually be. One of the leading hypotheses is that dark energy is an inherent property of space itself, a concept first proposed by Albert Einstein in the form of the cosmological constant. Einstein introduced the cosmological constant as a term in his equations to allow for a static universe. However, after Hubble's discovery of an expanding universe, Einstein discarded the cosmological constant, considering it his biggest blunder. Ironically, this concept was revived decades later, as scientists found it useful to explain dark energy's effect on the universe. If dark energy is indeed the cosmological constant, it means that as space expands, new space comes with its own inherent energy, continuously adding to the universe's total dark energy. This interpretation fits with the observed acceleration of the universe's expansion. Essentially, the more space expands, the more dark energy there is, which further accelerates the expansion, a runaway process that will continue indefinitely unless some other cosmic phenomenon intervenes. Another theory posits that dark energy may be a type of field, often referred to as quintessence. Unlike the cosmological constant, which is a fixed value, quintessence is thought to be dynamic, potentially changing over time. This concept draws from the idea of fields in quantum mechanics, where particles and forces are described as excitations of underlying fields. If dark energy is indeed quintessence, it would mean that dark energy's effects on the universe could vary, potentially slowing down or speeding up over cosmic timescales. Quintessence, however, remains a highly theoretical concept, and scientists are still working on ways to test it. Another theory with roots in quantum mechanics suggests that dark energy might be linked to vacuum energy, a concept in which empty space isn't actually empty, but filled with fleeting particles and energy fluctuations. In quantum physics, particles are constantly appearing and disappearing, creating tiny bursts of energy. If the vacuum of space holds energy in this way, it could help explain the repulsive force attributed to dark energy. However, calculations involving vacuum energy lead to values that are astronomically higher than what we observe for dark energy, making it one of the great unsolved problems in physics. The existence of dark energy also raises fascinating questions about the ultimate fate of the universe. If dark energy continues to drive the universe's expansion indefinitely, the universe may face a big freeze or heat death, where galaxies drift so far apart that stars eventually burn out, leaving a cold, dark cosmos. Alternatively, some theories propose that if dark energy's effects change over time, it could lead to a big rip, where the repulsive force of dark energy becomes so strong that it tears galaxies, stars, planets, and even atoms apart. This catastrophic end scenario would mean that even fundamental particles would cease to exist in their current form. The study of dark energy remains one of the most active and challenging fields in cosmology. The quest to understand it has led scientists to build advanced telescopes, launch space probes, and develop sophisticated computer simulations. Projects like the Dark Energy Survey and the Euclid Space Telescope aim to map out the universe's structure and study how dark energy has influenced its expansion. These observations will help refine our understanding of dark energy's behavior over time and offer new insights into what might be driving this cosmic phenomenon. The concept of dark energy not only expands our understanding of the cosmos, but also challenges the limits of human knowledge. It reveals that we are only beginning to scratch the surface of the universe's mysteries, with many more questions left unanswered. In trying to understand dark energy, we find ourselves at the intersection of physics, philosophy, and the unknown, contemplating not only the nature of the universe, but also our place within it. Dark energy, in its vastness and mystery, reminds us that the universe is a place of boundless wonder and unanswered questions. As scientists continue their research, we may one day unlock the secrets of this enigmatic force, forever altering our understanding of the cosmos, and perhaps even of reality itself. Until then, dark energy remains a symbol of the unknown, a cosmic puzzle that beckons us to explore, question, and seek answers in the vastness of space. The story of dark matter and dark energy is a journey that spans decades, involving thousands of scientific minds working tirelessly to solve one of the biggest mysteries in cosmology. Both phenomena, though they remain largely invisible, have measurable effects on the universe, from the formation of galaxies to the acceleration of cosmic expansion. Scientists have developed theories, conducted experiments, and examined the most advanced evidence to attempt to understand these elusive forces. One of the most compelling pieces of evidence for dark matter comes from gravitational lensing, a phenomenon predicted by Einstein's theory of general relativity. Gravitational lensing occurs when the gravitational field of a massive object, such as a galaxy cluster, bends the light from objects behind it. This effect can be observed and measured, and it gives astronomers a way to see dark matter indirectly. In various observations, scientists have found that the amount of visible matter in galaxy clusters isn't enough to account for the gravitational lensing observed. This discrepancy suggests that there is additional, unseen mass contributing to the gravitational pull, which we attribute to dark matter. These lensing studies have helped confirm that dark matter exists and plays a significant role in the structure and behavior of galaxies. Furthermore, gravitational lensing allows astronomers to map the distribution of dark matter across the universe. By analyzing the distortion of light from distant galaxies, they can create mass maps that highlight areas where dark matter is concentrated. These maps have provided further confirmation of dark matter's influence, reinforcing the idea that it permeates the cosmos, acting as an invisible scaffold that holds galaxies and clusters together. Another critical piece of evidence supporting the existence of dark matter and dark energy comes from the cosmic microwave background, CMB radiation, the afterglow of the Big Bang. The CMB provides a snapshot of the early universe, revealing slight fluctuations in temperature and density that eventually led to the formation of galaxies and larger cosmic structures. Through observations from satellites like NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and the European Space Agency's Planck mission, scientists have been able to measure these fluctuations with incredible precision. The data shows that ordinary matter alone cannot account for the density and distribution of the cosmic structures we see today. When scientists plug these measurements into cosmological models, the only way to make the models align with observations is by including dark matter and dark energy. The CMB data not only provides evidence for dark matter, but also supports the presence of dark energy. The rate of expansion of the universe, as indicated by CMB measurements, suggests a significant amount of extra energy in the cosmos that doesn't come from visible or dark matter. This invisible force pushing the universe to expand at an accelerating rate is attributed to dark energy. Another fascinating line of evidence for dark matter comes from studying the rotation curves of galaxies. In the 1970s, astronomer Vera Rubin observed that stars and galaxies were orbiting their centers at unexpectedly high speeds, regardless of their distance from the galactic center. According to Newtonian physics, the gravitational pull of visible matter should cause stars farther from the center to rotate more slowly, similar to how planets orbit slower the farther they are from the sun. However, Rubin's observations revealed that stars on the outskirts of galaxies were rotating at nearly the same speed as those closer to the center. This phenomenon, known as a flat rotation curve, implies that there must be more mass in galaxies than what we can see. This missing mass is dark matter, which provides the additional gravitational force necessary to keep the outer stars in orbit at their observed speeds. Galaxy rotation curves have become one of the most straightforward and compelling pieces of evidence for dark matter, confirming its presence across numerous galaxies. Without dark matter, galaxies would not have the gravitational stability to maintain their observed structure. Theoretical physicists have developed several models to explain dark matter and dark energy, although each comes with its challenges. For dark matter, there are two primary candidates: weakly interacting massive particles, WIMPs, and axions. WIMPs are hypothetical particles that interact only through the weak nuclear force and gravity, making them difficult to detect. They are thought to have been created in the early universe and could make up the missing mass required to explain dark matter's gravitational effects. However, despite numerous experiments, including detectors located deep underground and in particle accelerators, WIMPs have yet to be directly observed, leaving their existence unconfirmed. Axions are another proposed candidate for dark matter. These are extremely light particles that also interact weakly with normal matter. Axion experiments, which involve using high-powered magnetic fields to convert axions into detectable photons, have been ongoing. While there have been some intriguing hints, no definitive evidence of axions has been found yet. As for dark energy, one of the primary theoretical explanations is the cosmological constant, as mentioned in earlier chapters. However, other theories propose that dark energy could be the result of a dynamical field, akin to a scalar field, that changes over time. This concept, called quintessence, differs from the cosmological constant, which has a fixed value. Quintessence would imply that dark energy's influence might fluctuate, leading to different expansion rates in the future. The study of dark matter and dark energy is fraught with challenges, both technical and theoretical. One of the biggest obstacles is that these phenomena do not interact with light, making them effectively invisible and difficult to study directly. Scientists must rely on indirect methods, such as gravitational effects, to gather clues about their nature. Another challenge lies in the limitations of current technology. Detecting particles as elusive as WIMPs or axions requires advanced detectors, often located deep underground to shield them from background noise. Experiments like the Large Underground Xenon (LUX) experiment and the Axion Dark Matter experiment (ADMX) have pushed the boundaries of particle detection, but the lack of direct evidence continues to pose questions. Furthermore, dark energy research faces theoretical challenges. Explaining the nature of dark energy requires reconciling quantum mechanics with general relativity, two foundational theories of physics that remain incompatible in their current forms. A unified theory of quantum gravity might hold the key to understanding dark energy, but such a theory remains one of the holy grails of theoretical physics. Finally, there are philosophical challenges that complicate our understanding of dark matter and dark energy. These phenomena force us to confront the possibility that the universe is not entirely knowable. They challenge our assumptions about the nature of reality and the limits of human perception, raising profound questions about the nature of existence and our place within the cosmos. In conclusion, the evidence for dark matter and dark energy is compelling, from gravitational lensing to the cosmic microwave background and galaxy rotation curves. Theoretical models provide potential explanations, but many questions remain unanswered. As technology advances and new discoveries are made, we may come closer to unraveling the mysteries of dark matter and dark energy. However, for now, they remain as enigmatic as ever, serving as a reminder of the vast unknowns that still lie within the universe. The impact of dark matter and dark energy on the cosmos extends far beyond simply filling in gaps in our understanding. These unseen forces are critical to the very fabric and formation of the universe. From how galaxies form and cluster to the evolution of large-scale structures across billions of years, dark matter and dark energy play defining roles in shaping the cosmic landscape. One of the most intriguing roles of dark matter is its function as a kind of cosmic framework or scaffold that organizes the visible matter we see in galaxies, stars, and nebulae. In the early universe, moments after the Big Bang, tiny fluctuations in density began to form, seeding the first structures. Dark matter, unaffected by electromagnetic forces, did not experience the drag of radiation that visible matter did, allowing it to start clustering much earlier. This early clustering of dark matter acted as gravitational wells that drew in regular matter, encouraging the formation of galaxies within these invisible structures. As time went on, these clumps of dark matter grew in size and merged to create even larger structures. Today, the galaxies we observe are merely the tip of the iceberg, visible markers of far larger dark matter halos. Without dark matter, galaxies would likely have taken far longer to form, or they might not have formed in the same way at all. This means dark matter's influence on cosmic evolution is profound and foundational. A galaxy's shape, size, and distribution are influenced by the underlying dark matter halo in which it resides. These halos of dark matter envelop galaxies, binding stars and other matter gravitationally and providing the extra mass required to stabilize the galaxy. For instance, in spiral galaxies like our Milky Way, the gravitational effect of dark matter keeps stars rotating at high speeds even in regions where visible matter is sparse. Dark matter halos not only affect individual galaxies, but also influence how galaxies cluster together in groups and superclusters. Observations show that galaxies tend to form in dense regions where dark matter is concentrated, with filaments connecting clusters across vast stretches of space, forming a cosmic web structure. This large-scale structure of the universe, clusters of galaxies connected by filaments of dark matter with vast voids in between, is one of the most compelling pieces of evidence for the influence of dark matter on a cosmic scale. While dark matter helps structure the cosmos on a smaller scale, dark energy plays a contrasting role on the largest scales, driving the accelerated expansion of the universe. This expansion affects not just the fate of individual galaxies, but the destiny of the universe as a whole. Since the discovery of cosmic acceleration in the late 1990s, scientists have understood that dark energy constitutes a significant portion of the universe's energy budget, around 68%, compared to dark matter's 27% and regular matter's 5%. Dark energy's influence becomes especially apparent over large distances, where its repulsive force begins to outweigh the gravitational pull of dark matter and visible matter. This accelerated expansion impacts how galaxies move relative to each other and alters our understanding of cosmic evolution. Without dark energy, the universe might have continued to expand at a slower rate, or depending on the balance of forces, might eventually have collapsed back on itself in a big crunch. Instead, dark energy pushes galaxies apart at an accelerating rate, suggesting a potential big freeze scenario in which the universe cools and stretches endlessly. In a universe dominated by dark energy, the long-term fate of galaxies and galaxy clusters is one of isolation. As the universe expands faster and faster, galaxies that aren't gravitationally bound to each other will move apart at such high speeds that they'll eventually cross a kind of cosmic horizon, becoming inaccessible from one another. This accelerated separation means that over billions of years, galaxies will find themselves increasingly isolated, with distant galaxies moving beyond the reach of any observer. In this future, local galaxy clusters like the Milky Way's local group will become the only accessible regions of the cosmos. Stars will continue to form for some time, but as resources are depleted and cosmic expansion proceeds, the light from most of the universe will fade, leaving a dark, cold expanse. This fate, often referred to as heat death, is an inevitable consequence of dark energy if its influence remains constant or increases. Despite the influence that dark matter and dark energy clearly have on the cosmos, many open questions remain. Scientists continue to explore alternative models that might help reconcile inconsistencies or unexplained observations. For instance, modified gravity theories propose that instead of dark matter and dark energy, we might need a new understanding of how gravity behaves at large scales. There are also questions about the nature of dark energy. Could it evolve or decay over time, leading to an eventual big rip, where even atoms are torn apart? Or might it one day reverse, causing the universe to contract? Such ideas, while speculative, remind us that our understanding of dark matter and dark energy is still developing, and as we gain more insights, our view of the cosmos and our place within it may continue to shift. In summary, dark matter and dark energy are not mere scientific curiosities. They shape every corner of the cosmos, from the smallest galaxies to the vastness of intergalactic space. They offer glimpses into the universe's past, illuminate the structures we observe today, and hint at a future where galaxies drift into isolation. Through ongoing exploration, scientists hope to unlock further mysteries about these invisible forces that so profoundly influence our universe. As we draw this journey to a close, we're left with a sense of awe and perhaps a little wonder about the vast unknowns of our universe. Dark matter and dark energy represent mysteries that defy our understanding, yet they shape everything we see, and even what we can't see. These invisible forces don't just reside in the distant cosmos. They weave through galaxies, affect the formation of stars, and silently guide the evolution of everything around us, from the smallest particles to the entire universe. Our exploration into dark matter and dark energy raises profound questions that touch on the edges of science, philosophy, and even our own sense of purpose. They remind us of our small place in a universe governed by forces that are largely hidden from us, yet so fundamental to reality itself. Every new piece of evidence, every fresh insight, takes us closer to a deeper understanding of the fabric of existence. The allure of the unknown is a powerful call, and as we look to the stars, we're drawn to explore, to question, and to understand. Dark matter and dark energy are just two pieces of a much larger puzzle. They challenge us to stretch the limits of our knowledge, to go beyond the observable, and to imagine the unimaginable. Each discovery peels back another layer of cosmic mystery, revealing not just answers, but more questions, questions that inspire us, that make us question the very nature of reality. If you've enjoyed this exploration of cosmic mysteries, remember to like this video and subscribe to the Storyteller Panda for more thought-provoking journeys into the wonders of the universe. We invite you to share your thoughts in the comments below. Do you believe we'll one day understand the true nature of dark matter and dark energy? And if so, what might that reveal about our own existence? Also, don't miss out on our other videos, which will appear on your screen now. They dive even deeper into the hidden dimensions of our universe. So click on them and continue this journey with us. Thank you for watching, and we'll see you in the next cosmic adventure.